The problem from GATE Physics 2018 reads as follows. A p-doped semiconductor slab carries a current I equal to 100 milliamps in a magnetic field B equal to zero point 0.2 Tesla as shown. One measures Vy equal to 0.25 millivolts and Vx equal to 2 millivolts. The mobility of holes in the semiconductors is, and the units are meter square per volt second. And since it's a numerical answer type question, we are required to round off our answer to 2 decimal places. And this is the slab that has been given with the dimensions that are mentioned here. I've just noted all the relevant information, and the slab has been read on here. Now note that the current is flowing from left to right. So the Vx, this thing is the cause of the flow of current in this direction is this applied potential Vx. So we can also write that Vx is nothing but our applied potential, right? Thus this will be our Hall voltage. Since it's a p type, so the majority, almost all the current will be carried by holes, and since the current is in left to right, the holes will also be traveling from left to right, and there is a pointing downwards magnetic field, and correspondingly the holes will migrate to one end and thus giving rise to Hall voltage. Now I can write that the Lorentz force on holes, the magnitude of it will be Q V of holes times B. I'm writing just the magnitude. So at steady state, the so let me rewrite it. Let me correct myself a bit. So let's erase this. Okay. So what we can say is that at steady state, Lorentz force should be balanced by the Coulombic force due to Hall voltage. Coulombic force due to Hall voltage. Note that this we are talking about force in this direction into the plane of the paper. So Lorentz force can be written as Q V B, the magnitude of it. So we are only talking the magnitudes because direction will be opposite, obviously. And the Coulombic force due to Hall voltage would be Q times the electric field due to Hall voltage. I'm writing it as EH. So Q and Q get cancelled. So what I get is, so this is only, since there's only holes in the system, so we write VH times B equal to EH. Now we know that V will drift velocity, VH is nothing but the drift velocity in this direction, VH will be nothing but mu H times applied field, E applied. VH is nothing but mu H times E applied. So this will be mu H times E applied is nothing but V by L, Vx, because Vx is the applied potential times the length. This, because this is the length along which the holes are traveling, right? And similarly, I can write EH is nothing but VH divided by Hall potential is generated across this front and back, divided by W, the width of the semiconductor slab. So I'll replace VH from here to here and EH from here to here. Okay, so VH is nothing but Vy over W. So this expression that we wrote then becomes, the value of VH is mu H times Vx over L and into B, this expression equal to EH. EH is nothing but Vy over W. So rearranging the terms, I get mu H equal to Vy into L divided by Vx into B into W. I'll just now put the values. So value of Vy is given to us 0.25 millivolts times length is given as 10 mm, 10 mm divided by Vx is 2 millivolts, 2 millivolts times B is zero point 0.2 Tesla, 0.2 Tesla. W is 4 mm, 4 mm. So mm gets cancelled, millivolt gets cancelled. What we do get here is, so 0.25, so I can write it as 1 by 4. So this will be 100 divided by 4 into 2 is 8, 8 into 16, 16 into 4 64, 64. So that is 1.5625. So it's SI units, meter square per volt second, because everything is in SI units here. So because got cancelled, and again millivolt got cancelled, so everything is in SI units. So the value of mu h I got was 1.5625. Okay. So we were required only 2 decimal places, so if I round it off, it will be 1.56, right? So that is the answer that we have arrived at. Thank you for listening.